Hello guys, this is SHUBHAM Shinde and I am again with a new lecture series on work, power and energy. The work, power and energy is a very important topic which is concerned with your NEET examination. So this work, power and energy, the questions in the exams from this chapter are pure questions from work, power and energy, as well as the applications of this work, power and energy will be used in various different topics such as electromagnetic induction, magnetic effect of electric current and many other topics such as circular motion also. So it is a prime concern to learn this topic in a very detailed manner as we are going to do it today. So I hope that you like these lectures and you will get benefited from this lecture series. Okay, so now I'll write the heading of the topic, that is work, power and energy. So this is the heading of the topic we are going to learn, work, power and energy. At the beginning of the topic, you are the beginners and you will think that work, power and energy, these are very different terms. But after learning this chapter, you will understand that these three terms are not very different. They are similar terms, just they are separated by some definitions and some conditions. But these three terms, work, power and energy, are very much linked to each other. The work you do is going to get converted into energy, which also can convert it to power. So these three terms, work, power and energy, are very similar to each other and will be used as per the condition and consequences. Okay, so now we'll start with the very first topic, that is the work. Okay, so now we'll learn what is work. So what is work? So from a general definition, the work you do is you play, you do any work, you study, this you'll call as a work. But in physics, the work or the definition of work is slightly different. So what is work? Work is nothing but the scalar product of force and displacement. So what does it mean? Work, which is denoted by W, is equals to the scalar product of force dot ds. Okay, so what is F? F is nothing but the force which is applied on any body. And what is ds? Ds is the displacement, okay, through which the body is traversing. Okay, so the scalar product of force and displacement is work. So you will say that work is nothing but the scalar product of force and displacement. I also can say that if this is a body, this is a body, okay, and now suppose I am applying a force of F in this direction, okay, so this is a force which I am applying on this body. Suppose due to this force my body is getting shifted to this new position and the distance between both the position is ds. So what will be my work? The work will be F work is equals to F dot ds. Okay, so when I expand this, what is it? F ds cos theta, where theta is the angle between the force and the displacement vector. Okay, so now we are going to see what is the vector form or the vector angle. Okay, so now this is the body, okay, this is the body and this is the force, okay, and this is the displacement. Now see that this force, so this is direction of force, this is the direction of force. What is the direction of displacement? Direction of displacement, I'll write it with white color, is also in this direction, that is ds. So now you can see the angle between the force as well as the displacement is 0. So the theta is going to be 0. Now I put this theta in this formula. So what will this formula be? So it is F ds cos 0. What is the value of cos 0? The value of cos 0 is nothing but 1. So my work will be F dot ds. So here it is simply magnitude of force into magnitude of displacement. Okay. So this is the general idea of what is the work. Okay. Now we are going to see a slightly connected topic, that is work done by a constant force. So what does a constant force means? What does the constant force means? I know force. This force is a vector. And vector has two aspects. One is the magnitude and another is the direction. So a vector has magnitude and a direction. So any of these, if any of these will change, the velocity, the force vector is going to change. Means suppose for a journey of 5 seconds, suppose now a body, I am pushing the body and I am pushing the body for 5 seconds. So suppose for whole 5 seconds, if my force remains constant, suppose it is 5 newtons. For 5 seconds, the force remains throughout 5 newtons, then I can say it is a constant force. But one thing is important, that its direction should not change throughout the whole process. This is a very important thing. Means I want to say that for a vector not to change, its magnitude as well as its directions needs to be same throughout the journey. And such a force is called as a constant force. Now we will see what is work done by such a constant force. It is simple. It is W is equals to F dot ds, or I can write F ds cos theta. So this is the same as we have previously seen. Now we will be shifting to the another topic, which is the work done by a variable force. Okay. So what is work done by a variable force? I am highlighting this variable. What does this variable means? Variable force, again I can say that force is a vector. Force is a vector. It has two aspects. It has a magnitude and it has a direction. If magnitude changes, force will change. If direction will change, force is going to change. So I can say if any of these changes, the force is going to change. Suppose I am pushing a box for a time of 5 seconds. Suppose for initial 2 seconds I am shifting the box with 2 newtons. For next 2 seconds I am shifting the box with 3 newtons, and for next 1 second I am shifting the box with 1 newton. So can you see that the force is changing, or magnitude of force is changing? And I can say if the magnitude of force is changing, the force is going to change. Hence I can say it is a variable force. Okay. Now suppose in the same example, the box I am pushing for 5 seconds. Suppose for first 2 seconds I apply a force in a right direction. For next 2 seconds I apply a force in the left direction. And for next 1 second I apply the force from back side or from any other side. So you can see that throughout the process, the direction of my force which I am applying is changing at each and every point. So again I can say the direction of force is changing, and hence it is a variable force. So a force whose direction or magnitude changes is called as a variable force. And we are going to find here the work done by the variable force. So you have understood now what is variable means. Variable means whose direction and magnitude changes in the process of shifting the blocks. So how can we find the work done by a variable force? because we only know the formula of work done by a constant force, and that is equals to W is equals to F dot ds is equals to F dot ds dot cos theta. So you can see from that equation, for that 2 seconds my force was constant. For next 2 seconds my force was different from the first 2 seconds but was constant throughout that 2 seconds. Similarly, I can say, now tell me, this is a curved line, this is a curved line, okay? So I cut this curved line into very small pieces, very small pieces, and I go on cutting and go on cutting and go on cutting up till I get a small part which is not a curved line but it is a straight line. Now I cut it very small and I'll take this part here, and I can see that this is a small straight line, it is not a curved line. And all these infinitesimally small parts are all straight lines which are joined to each other to form this curved line. Means I can say, even though this line is a curved line, but when I divide it into millions and billions of parts, each one of the infinitesimal part is going to be a straight line irrespective of what it forms in a whole. Similarly, I can say in this equation, suppose a particle, suppose a box which is present here and is going to go here, okay? In this whole journey, I don't know at which point what is the force and what is its direction, because I know that the force is variable. It is going to change at each and every point and each at every angle. So how can I find out what is the work done? So we'll see what can be done. I again previously told you that that was a curved line, but if I want to find the length of that curved line, I can't find it. But if I divide that curved line into small pieces such that that infinitesimally small piece is not now a curved line, now it is a simple straight line. Now I can measure the length of the straight line, and I'll measure the length of all the straight lines, single straight infinitesimally straight lines, and I'll add that length and I'll get the length of whole curved path. Similarly, here you have this journey from point A to point B, and I don't know that the force which is acting is constant or not, it is variable. So how will I find what is the total work? Hence I am going to divide this whole journey into small infinitesimally small parts, such that when I see a infinitesimally small part, I'll see that the force in that particular part is constant. I know that from this point to this point the force is not going to remain constant, but if I divide it into infinitesimally small part such that even though for the whole journey the force is not constant, but for that infinitesimally small part the force is going to remain constant in direction as well as in magnitude, okay? So for that infinitesimally small point or small part, I can find out the work by the formula which I know, the formula of finding work by constant force, and that is W is equals to F ds cos theta. मतलब कि अगर ये जर्नी में फोर्स अलग अलग है सब पॉइंट पे, तो मैं उसका वर्क कैसे निकालूंगा? तो सिंपल है, आपको इस पूरे जर्नी को छोटे छोटे टुकड़ों में काटना है, और ऐसे काटना है कि जो छोटा टुकड़ा बन जाए उसके लिए, सिर्फ उसके लिए फोर्स कांस्टेंट हो, और आपको फोर्स कांस्टेंट होने पर वर्क तो आराम से निकल जाएगा। वो कैसे निकालोगे आप? W इज इक्वल्स टू एफ डी एस कॉस थीटा। तो इसी तरीके से आपने उस इनफाइनाइटेसिमली स्मॉल पार्ट का वर्क फाइंड किया। तो अब क्या करोगे? अगले पार्ट का निकालोगे। ऐसे करते करते आपने जब सब पार्ट्स का निकाल लोगे वर्क, तो उसको ऐड कर दो। और हम इस एडिशन को सिर्फ एडिशन नहीं बोलते, वी कॉल इट एज इंटीग्रेशन। So this is what is integration. Integration means finding the work of each and every small part and bringing them together to find the total work of whole journey, and this is nothing but the integration. So I want you to understand that we are going to perform a simple integration in which we will divide this whole journey into small infinitesimal part, for each one of which the force is going to remain constant, we are going to equate the work with the formula W is equals to F ds cos theta. We are going to add all such works, such small works, we will call dW. Why dW? Because they are small works, and when I'll equate all the works, I'll call it as a capital W. Okay. So now suppose this is point A, this is point B, and this is the force which I am applying, dF. So now I know the particle is going to go from A point to B point. Okay. Now suppose I'll divide this whole journey into small parts, infinitesimally small points, such that for this, now suppose this point, so now for this journey I'll magnify it. So for this journey the force is going to remain constant. Understanding? Means the force here is something F1, it is going to F2 here, it is going to be F3 here, it is going to change. But I can say that force, even if it changes for whole journey, but for this much part the force is going to remain constant. So I can write work for this much part W, but it will be a dW because it is a small work. dW is equals to F dot ds, small displacement. Okay. So in this way I have found out the work of this much small part. So I can in similar way find out the works of such all parts. When I've got the work of all such parts, then I can equate it, or I can add it in a simple way. I can integrate it. So next thing is I'll integrate such all works and I'll get a total work by integration of all such works, dW. So by integrating, what we will get is integration of F ds. So we will get is from, so ds changes from S, from point A to point B. So in this way you can find out by integration what is the work done in whole journey by a variable force. Understanding? So in this way we have learned what is the work done by a variable force. Now we will see what is the work done in the form of Cartesian. Okay. So work in the Cartesian form. Suppose the particle now not only moves in a x and y direction, but it also moves in a z direction. So what will be the total force? So we'll find it out with the help of the Cartesian form, which is very simple. Suppose the force is Fx I cap plus Fy j cap plus Fz k cap. Okay, and the point has moved from point S1 to point S2. Okay, now I'll write this S1 as S1 is equals to Sx I cap plus Sy j cap plus Sz k cap, and I'll write this S2 as S2 is equals to S2 I cap plus S2 j cap plus S2 k cap. Okay. Now the particle is going to move from here to here. So what is the work done? This is the Cartesian form of work. Okay. So how will we solve this? It is very simple. I know the variable force. So can you tell me how can we find the work done from a constant force through using the formula of work done by the variable force? The thing is very simple. The thing work done by constant force is a special condition of the work done by the variable force. Okay, so you can just find out the work done by constant force by putting the value of F constant, like you have work by a variable force is equals to F dot ds. Suppose now force here is constant. Okay, so force is constant. So what will happen is that the force being a constant value will come out of the integration. So it will be F dot ds. So now it is simple to the formula which you have learned earlier, that S1 and S2. So it is W is equals to Fs, which is similar to the work done by a constant force. So this is how we have understood how we get one formula from the other formula. Okay, now we are going to use the work done by the variable force as a formula, and now we'll see what is the equation when we find the work. Now we'll understand with the help of a graph. So suppose this is a graph and the particle is initially at point S1. The particle now goes to point S2. So S1 is the initial position, S2 is the final position. Suppose the coordinates of S1 point are x1, y1, z1, and for S2 point it are x2, y2, z2. So I am not interested in S1 or S2, I am interested in ds, or change in distance, or change in displacement, or I am simply displacement. So I am interested in ds. So what will be ds? ds will be x2 minus x1, y2 minus y1, and z2 minus z1. So if I write it, ds is equals to dx I cap. So it is the change in displacement along the x-axis. So I have written I cap. dy, it is the change along y-axis. So I have written j cap, and dz is the change in displacement along z-axis. So I have written k cap. So in this way I have written ds, and I know the force. So I am going to write the work done. So what will be the work done? The work done is equals to F integration of F dot ds. So what is force? So force is Fx I cap plus Fy j cap plus Fz k cap dot dx I cap plus dy j cap plus dz k cap. So this is how I have written the formula. Now this is a scalar product, and you know, for a scalar product you have to just mix this whole terms, and finally x will go with x, y will go with y, and z will go with z. This is a small hint you can know to solve this scalar product. So I can write work done is equals to integration of fx dx plus fy dy plus integration of fz dz. So this is a simple thing you can do to find out the work done in the form of Cartesian coordinates. So this is how we have completed the Cartesian coordinates, and we'll now move toward the next topic. Okay. Now, from a numerical point of view, or the questions which you are going to ask to you in the examination, one most important question which we shall not forget to see is the equations which can be solved through graphical or graphs. Okay, so this is the graph. So now this is the force. Okay, so y-axis represents the force, and x-axis will represent the displacement or simple position. Now suppose the particle, now I'll draw a graph. Okay, so now suppose the graph comes in this way. Okay, so graph comes in this way. So initially the particle is, suppose you start your experiment from point R1, okay, and your point goes up to position R2. So your journey of the particle goes from point R1 to point R2, okay. So how will you find from this graph the work done from point R1 to point R2? So it is very simple. Again, I know whenever the force, you can see along the y-axis, the force at each and every point is changing. So this is the condition of a variable force. And I know how can we solve the condition of variable force. It is through simple concept of integration. So we'll integrate this term. And I know before integrating, what have I to do is, I'll break this whole journey from R1 to point R2. I'll break this whole journey into small particles or small parts. And I'll find the work of each single part through a formula of constant force, and I'll then add or integrate all these terms to find the work of whole process. But this was a theoretical concept. How can we do it in the form when it is a graph? So if I say a particle, if I divide this journey into small parts, there will be a small part here, okay? Suppose this is the part, one of the part, infinitesimal part, and now we have to find work done for this infinitesimal part, such that the force remain constant for this infinitesimal part, okay. So I'll extrapolate this graph. I have drawn this graph or this slit, a very wide one, because you have to understand. But for an infinitesimal small change, this slit will be very small, okay. Now I color this. Slit, okay. So this is the, suppose this is the small change in positions, or this is the small displacement. So I know that dW, small work done for this portion, yellow portion, is equals to F dot dr. So tell me, what can you infer from this formula? That this work done, which you can find from the formula theoretically, here it is equals to the area of graph. So whenever there will be a graphical question, you can find the area under the graph, okay. So what will be the dW? dW is this much area, which is in the yellow color, okay. So dW is the area in yellow color. So this much area for this much displacement. So I can say that if I extrapolate this graph from R1 up till R2, so this whole area is my area under the curve, and I can call it as the total work. So I can say that work done by the force, which is variable, for pushing a point from point R1 to point R2 is nothing but equals to area under the curve. Okay, so it is very simple. So in this way you can give your answer for the questions which are based upon the graphical questions. Simply they'll ask you what is the work done between these 2 points. You have to just find the area between these 2 points and the area under the curve, and that will be your work done by the variable force from that point to the next point. So in this way we have covered a major section on the introduction. Okay, I hope you have understood it, and now we'll go to our next topic. Okay, so now we'll see different types of works: a positive work, a negative work, and a zero work. So are these very different? No, these are not very different. These are different only for this differ only in a small point, that is the theta. What is a positive work, what is a negative work, and what is a zero work, we shall see with some examples. So first we'll see the positive work. So what is a positive work? positive work. So suppose this is a block. This is a block. Okay. Now the force which I am applying is in this direction. Okay. So I am applying a force from this direction. Now the particle or the box is going to move in this direction and it will reach at this point. Okay. So I can say this ds is in horizontal direction and force is in this direction. So ds is in horizontal direction. So whenever I write theta, so tell me what will be the theta. So this is going to be the theta between the force vector and the ds vector. So tell me whether the theta is greater than 90 degree or less than 90 degree. So the theta is surely less than 90 degree. That means the theta is an acute angle. The theta is an acute angle. Okay. So whenever I write work done is equals to F ds cos theta. So I know for theta the value is going to be less than 90 degree. Suppose I now make a graph of cos function. So what is a cos function? Cos function starts here, it goes up. So this is the graph of a cos function. So cos function, this is the degrees. So this is 0 degree. This is 90 degree. Okay, this is 180 degree. This is 360 degree. So you can see that before 90 degree, the value of cos is above the x-axis. Okay, this means that for all the theta which are less than 90 degree, the cos theta is going to be positive. Okay, so means for this condition the cos theta is going to remain positive, and surely the force and ds are going to be positive. So I can say that whole work is going to be a positive value. Okay, and its magnitude is going to be F ds cos theta. So you have to understand that this is the graph of a cos function. It starts from value 1 at 0 degrees. Okay, and at 90 degree is equals to 0. So for all the values of theta less than 90 degree, the value of cos theta will be positive. Okay, as you can see here, the graph or the yellow shaded part is above the x-axis. So for all value of theta less than 90 degree, the cos theta is going to remain positive, and hence the work done here is positive. So I can see that the work is positive, or this is a positive work. So when can I say this? When the theta or the angle between the force and the displacement is less than 90 degree. Okay, now we'll see it with an example. Suppose example is body falling under gravity. Okay, so suppose I have a ball and I release the ball from a certain height. It is going to go down. So which is the force which is acting on it? It is the gravity. So I'll ask, what is the work done by the gravity? So work done by gravity is equals to gravitational force. So I'll write Fg into displacement into cos theta. So I'll draw a diagram. This is the body. Okay, this is the body. Tell me where is the direction of force. The direction of force is in the downward direction. So I'll write Fg in the downward direction. Tell me what is the direction of displacement. So the body is going to go down, so the displacement will be also vertical in nature. So this is the displacement. So now tell me what is the angle between Fg and S. So the angle is the thing but 0 degree. So theta, I will write it as 0 degree. So when theta is 0, I know from this graph the value of cos theta or value of cos 0 is going to go 1. which is a positive value, because I have told for any value of theta which is less than 90 degree, the value of cos theta is going to be positive. So this cos theta is a positive value and its magnitude is 1. So my work is going to be Fg into ds, which is an example of a positive work. So now we know what is a positive work, and we know that for all angles which is less than 90 degree, the work is going to be a positive work. Example is the body falling under gravity. So now we are going to see next what is the negative force. You will have understood what I will be telling next. Okay, simply when the theta goes more than 90 degree, or force and ds acts opposite to each other, the work will be negative. We will see it shortly. So negative work. Now this is the body, okay, and now suppose this is the initial position A, this is the final position B. The displacement is ds, okay, and the force is acting in this direction, okay. So tell me, where is the direction of ds? The direction of ds is in this direction or horizontal direction, and this is the direction of force. So tell me, this is the theta. What will be the value of theta here? The value of theta, this is an obtuse angle and it is going to be surely greater than 90 degree. Okay, so I can write value of theta is greater than 90 degree. Okay. So for such things, what will be the formula? So it is greater than 90. I can say it is an obtuse angle. Okay. So when I write W is equals to F ds cos theta, where theta is greater than 90 degree, and I know from a cos function that for values greater than 90 to 180, you can see between these 2 points the graph is going down below the x-axis. That means the values of theta which are greater than 90, the value of cos theta will be a negative. So I can say that value of this cos theta is a negative term. So I can say that work here is negative. Okay. So the work here in this case is negative. So I can say whenever the value of theta becomes more than 90 degree, okay, as depicted over here, the work done will be negative. Okay. So this is how we have understood what is the negative work, and we'll see it with the help of an example. So what is the example? Suppose you are going on a bike, or suppose this is a block. It is going here, so it is the ds, but the friction will act in the opposite direction. So this is the friction force. So what is the work done by the friction force? So work is equals to frictional force. So I write Ff into ds into cos theta. So tell me, this is the direction of ds. This is the direction of force due to friction. So the angle between these both is theta, which is 180 degree. And what is the value of 180 degree? It is a negative value, which is -1. So I can write work done is equals to negative term, negative, and that will be minus F dot ds. So in this way we have understood an example where we can see the work is negative. Okay. So now we will go to the next topic, that is the neutral work or zero work. So you can clearly understand from the title itself that it is a zero work. means the work done is 0. So can you tell me, work is F ds cos theta. So tell me, when will the work be 0? When this cos theta will be 0. So tell me, when will this cos theta be 0? Cos theta will be 0 when theta is equals to 90 degree, or the angle between the force and between the ds is going to be 90 degree, or I can say the force and ds are going to or should remain perpendicular. So in all such cases, the value of work is going to 0, and this will be called as a 0 work, or the work is 0. So this is the thing which I have told in the opposite manner. So when I tell it in a simple manner, when this force I am applying on a body, suppose now this is the body, okay? So this is the body. So ds is suppose here, and the force is here. So here you can say the angle theta is equals to 90 degree. So what is work? Work is equals to F ds cos theta. So theta, value of theta is 90 degree, and I know cos 90 is 0. So whole work is going to be 0. Understanding? So in this way you have understood what is a 0 work. Now we'll see what is the example. So when you go to a railway station, you will see a coolie over there who picks your luggage and drop you to the gate. So what he does is, he takes the luggage and he puts it upon his head, okay, and he walks. So now suppose this is the coolie, okay. So this is the coolie, okay, and he has luggage over his head, okay. So this is the luggage. So and he is going in this direction. So for the luggage, tell me, the coolie is applying a force on this luggage in a opposite direction or in a upper direction. So this is the force due to coolie, okay, and the displacement is here. So work done by coolie is equals to F of coolie into displacement into cos theta. Here I can see that theta is nothing but 90 degree. So work due to coolie is 0. Understanding? So this is the example where you will see the work done by coolie is 0. But my friends, even though the work done is 0, in a practical world he has done some work, just please give him his money, okay? So in this way we have understood what is the difference between positive work, the negative work, and the 0 work, okay?